AQA A Level Physics, and this is for the electronics option, and it's AM and FM. So consider an audio signal, frequencies up to about 20 kilohertz. Now, if you change that into a radio wave with a frequency of about 20 kilohertz, its wavelength would be 15 kilometers, and that would be impractical, because you would need transmitters which were about the same size. You would need receivers which were about the same size. Most aerials are like about a wavelength, about a quarter of a wavelength big, and it would just be bonkers. It would be impractical. So what you have is you have a carrier frequency, which is a much higher frequency wave which carries the signal, and we'll see how that is done in this video. There's two ways of doing it. You've got AM and FM. Now learn these wavelengths. Frequencies. Learn these frequencies. AM 500 kilohertz to about 1500 kilohertz. FM 88 megahertz to 110 megahertz. So FM is much higher frequencies than AM. And the original signal, which could be your audio signal, is modulated. It's changed before it's transmitted, and then it's demodulated after it's received, with this high frequency wave carrying the signal. So AM, we have the audio signal, and we have the high frequency carrier. So there's the audio signal, there's the high frequency carrier wave. They go through a thing called a modulator, and then this is the amplitude modulated wave. And if you look at the amplitude of this wave, you will see that it matches the original signal, the audio signal. We say that the high frequency signal is inside an envelope, and the envelope is the audio wave. If it was a digital signal, look at the diagram, it's pretty obvious how that would work. This is called a frequency spectrum, and it shows what frequencies are in a signal and their relative amplitudes. And if you had a single tone which was being carried by a high frequency signal, this would be the frequency spectrum. So in the middle, you've got your carrier frequency there, and then either side of it, if the tone was, let's say, 500 hertz, then you would have a line at plus or minus 500 hertz. Okay, so it's plus or minus FM. FM is the modulating frequency. Yeah, the modulating frequency, which is the audio. FC is the carrier frequency. And so this is a frequency spectrum. Be able to sketch it for the modulated wave. So the modulated wave is both of them together. Now that was if it was a single tone. If it was an actual audio signal, then that contains lots of different frequencies. And so the frequency spectrum would look like this. You'd have your carrier frequency again, but then you'd have these side bands, and upper and lower side bands, and they would be up to plus or minus FM. So that is the frequency spectrum, not to scale, for a modulated wave carrying an audio signal. Now, the frequency modulation, the modulating frequency, is limited to about 4 kilohertz. I said it was 20 kilohertz, but for music and speech, you don't need 20 kilohertz, particularly for speech. You can understand what somebody is saying with a bandwidth of about 4 kilohertz. Okay? If you use 20 kilohertz, then there wouldn't be enough bandwidth for very many channels. So that you can enable you to have different channels, you have a bandwidth of about a bandwidth of about 8 kilohertz, because it's 4 kilohertz either side. which comes to this equation. The bandwidth needed for each channel is 2 times the range of frequencies that you're using. So 8 kilohertz, 2 times 4 kilohertz is 8 kilohertz, and then you have 9 kilohertz gaps between the channels. I've seen a few times questions where you have to work out how many channels you can get within a wave band, and you just basically work out the bandwidth for each channel, and then you've got the gaps between them and divide the wave band by that. Now, frequency modulation. This is a bit more complicated, okay? And basically what we do is we change the frequency of a high frequency carrier wave. Yeah, the frequency of a high frequency carrier wave is varied. If we look at the high frequency carrier wave, there's the audio signal. It goes through the modulator, and notice this is the modulated wave, and you'll see that's a higher frequency, that's a lower frequency, that's a higher frequency, etc. Notice that the amplitude is constant, and we'll discuss the significance of that in a bit. Okay, now there are two components, two bits of information which need to be carried. It needs to carry information about the frequency, and it needs to carry information about the amplitude at any point in time. Now, the frequency of the modulating wave, yes, the audio wave, is shown by how, look, when the frequency changes of the carrier wave. So if you look where it's a peak there, the waves are closer together. Where it's a trough, these waves are further apart, and then it's a peak and they're closer together, and it's a trough. Yes, and so the variation of the frequency matches the audio frequency, and that is how you carry the information about the frequency. Yes. Now, how do you carry information about the amplitude? Well, the bigger the amplitude of the modulating frequency, then the bigger the deviation from the carrier frequency. If you look at this diagram, hopefully that will explain that. So from left to right, the amplitude is getting bigger. Now, see what difference it makes on the diagrams above. So the difference in frequency, or the deviation in frequency, there is quite small. Here, the deviation in frequency, the deviation meaning the difference between the frequency and the carrier frequency, notice it's getting bigger. And then on this last diagram, the deviation is quite big. There's quite a big difference between those two frequencies, that frequency and that frequency. Okay, and that's how you carry information about the amplitude in the frequency deviation. The frequency deviation is the difference in frequency between the wave at any instant and the carrier frequency. Now, if you were going to do all the frequency components needed to make up this signal, even if it's a single tone, even if it's our doo, yes, then this would be the frequency spectrum. You'd have lots and lots of harmonics, okay? And the bandwidth you would need for all of that would be very, very big. So practically, the frequency spectrum carrying a single modulating frequency, if you included all the components, then the required bandwidth would be impractically big. You couldn't have very many channels. So what you do is you limit the frequency deviation. The frequency deviation is limited to such that it carries 90% of the energy of the signal. Yes? For example, the BBC uses a frequency deviation of 75 kilohertz. And so that means that the frequency of the carrier is only allowed to deviate by 75 kilohertz. Okay? And you still get very, very good quality sound, but it limits the bandwidth. And that enables you to get more channels within the waveband. I appreciate I'm using lots of words here that I'm assuming that you understand, but there you go. Now, to work out the bandwidth, there's something called Carson's rule. So this is for FM, and the bandwidth is 2 times delta F. So delta F is the frequency deviation, and remember that's limited to 75 kilohertz, plus the modulating frequency, which is the frequency of the audio signal. Now, bear in mind that the signal is always stereo, and you have something called a pilot tone added as well. What's the pilot tone? Well, you don't really need to know this, but I'm not just going to chuck this word there without any explanation. The main signal, you've got your left and right channels actually added together. And the pilot tone carries the difference between the left and right channels. And so with the main signal and the pilot tone, you can actually process that and get your stereo. And if you don't process it, then you end up with mono. So both of them work. But basically the pilot tone carries the information needed so that you can separate the left and right channels of a stereo signal. So FM, including this pilot tone, is typically about 53 kilohertz. And so the bandwidth, and it would be worth remembering these numbers because I've seen them on exam questions, is 2 times 75 kilohertz, which is the maximum allowable frequency deviation, plus 53 kilohertz, 256 kilohertz. Okay. Then we need the gaps between the channels. We need 500 kilohertz gaps between the channels so that they don't interfere with each other. Have a go at this. How many stereo FM stations would fit in the waveband between 88 megahertz and 92 megahertz using the numbers above? Have a go yourself. The answer is... Okay, so 4,000 divided by our 500 gap plus our 256 bandwidth is 5.29, so 5. You could have 5 channels in that wave band. Remember this, advantages and disadvantages of FM over AM. So FM, high quality stereo, much better quality. You just on the radio in the car go between, BBC 5 Live, which would be AM on medium wave, and, Radio 1 VHF, and notice the difference, and it is significant. So high quality stereo, less prone to interference. Now, why? Interference is caused by stuff, electromagnetic stuff happening in the background. For example, sparks. Lightning can cause a lot of interference to an AM signal because these sparks produce bursts of electromagnetic waves, and machinery as well. FM was actually developed by the army because there was a big problem on the battlefield with communicating with AM because there was that much electromagnetic interference going on. The reason it's less prone to interference is because interference affects the amplitude of the signal. But in FM, the information isn't carried by the amplitude. So if you make the amplitude, after you've received the signal, if you make the amplitude constant again with something called a limiter, then you get your original signal without the noise. Okay? When the signal is received, its amplitude is made constant again. Disadvantages, FM modulation is more complex. It's more complicated than AM. The circuits are more complicated. Each station requires a bigger bandwidth. So you wouldn't have FM stations in the medium wave band. If you did that, you'd probably only have room for one station. So what you have you have it in a higher wave band. You use megahertz, 88 megahertz to 100 megahertz. The higher the frequency of the carrier waves, the more stations you can squeeze in. This is why for like satellite communication, you can have lots and lots and lots of channels because they use gigahertz. so you can squeeze in lots and lots of channels. FM uses the VHF band, very high frequency. AM uses the medium wave band. One little note might come up. If you're driving in your car and you go from one transmitter, the zone of one transmitter, to the zone of another transmitter, then will the two signals interfere with each other? And they might. So to avoid this, they actually transmit at slightly different frequencies, okay? And then your car's radio will automatically tune to the stronger signal. Yes, so your enjoyment of Radio 3 will not be disturbed as you go from one zone to the other. Here are the key points. Quite a technical little video this, I think, especially the FM stuff. AM, remember the frequencies, 500 kilohertz to 1500 kilohertz. We modulate the amplitude. So the amplitude of a high frequency carrier wave is modulated. To work out the bandwidth, it's just 2 times the modulating frequency, which typically 4 kilohertz. They don't use all of the 20 kilohertz that your ears can pick up, just 4 kilohertz. So typical bandwidth is about 8 kilohertz. It's a lot simpler than FM, needs much less bandwidth. Be able to sketch now the graph here with the upper and lower side bands, but remember for a single tone as well, where you just have the 2 lines there, those 2 components there. So be able to sketch those. It says in the specification you need to be able to. FM uses a much higher frequency carrier waves, 88 megahertz to 110 megahertz. The frequency of a high frequency carrier wave is modulated, so we're changing the frequency. To work out the bandwidth, it's 2 times delta F plus FM, where delta F is the frequency deviation, and that is limited. Okay, I said the BBC uses 75 kilohertz, and that's the maximum frequency deviation. Okay, high quality stereo, much less prone to interference. You know, lightning doesn't affect it at all. Why? Because it'll only change the amplitude, it doesn't change the frequency. And then you should be able to sketch this graph here that I talked about, which is all the different harmonics that make up the modulated wave, but then we are limiting it to delta F either side. So that's the maximum allowable frequency deviation. The frequency deviation being the difference in frequency between the wave at any instant and the carrier wave, and that is limited to about 75 kilohertz. And that's it. That's all of the electronics. I very much enjoyed making these. I found it very interesting. I hope you've enjoyed them. Another resource, and I did a lot of revision using this. If you Google AQA Teaching Guide Electronics, you'll find a document which contains everything you need to know and a little bit more. I would also say definitely look up as many past papers, and that will give you an idea of the questions that they're going to ask, obviously. And if you know your stuff, you'll see that they're all pretty straightforward. Anyway, good luck with that.